Welcome to episode 13 of the Pulse of Physiology podcast. I'm your host, Dr. Jim Davis, and today we're continuing our journey through the nervous system and diving into the fascinating topic of refractory periods. These brief phases during and after an action potential are essential for controlling how neurons communicate and preventing signal overlap. In our next episode, we'll explore the physiology behind chemical synapses, but for now, let's focus on the refractory periods. So what is a refractory period? Simply put, a refractory period is a short phase following an action potential during which a neuron's ability to generate another action potential is limited or even impossible. Refractory periods are critical for ensuring the unidirectional flow of electrical signals and preventing excessive firing. There are two types of refractory periods, the absolute refractory period and the relative refractory period. During the absolute refractory period, it is impossible for the neuron to fire another action potential, no matter how strong the stimulus. Here's why that's the case. Sodium activation gates are open. During depolarization, these activation gates on sodium channels are already open, so they cannot open further. And remember, these activation gates, or the opening of these activation gates, is what actually initiates the action potential. Additionally, during repolarization, the sodium inactivation gates have been closed, which prevents sodium from entering into the cell. These gates remain closed until the membrane potential returns near its resting state. So during depolarization, gates are open and we can't reopen them. And during repolarization, there are some gates that are closed that will remain closed until our membrane potential becomes more negative. Ultimately, when thinking about the absolute refractory period, think of it as if you're trying to flush a toilet that hasn't refilled yet. It simply won't work, and you're just sitting there jiggling the handle. You're not going to get another flush. Now we have the relative refractory period. During this period, a neuron can generate another action potential, but only if we have an unusually strong stimulus. Here's why. During repolarization, the potassium channels remain open. So potassium efflux continues during hyperpolarization, making the inside of the cell more negative than its resting potential. However, as we mentioned a moment ago, the sodium channels have reset. The inactivation gates are open and the activation gates are closed. But the hyperpolarized state, meaning more negative than normal, requires a stronger than normal stimulus to reach that threshold. And since the sodium gates have reset, if we have a large enough stimulus, we can reach threshold and then an action potential occurs. This is like when you flush a toilet with extra effort to try and get it to flush before it has fully reset. There's enough water in there that you can cause it to flush, which is a little bit different than when you try and flush it immediately after. Ultimately, refractory periods serve several important purposes. They control signal timing by limiting how quickly a neuron can fire. These refractory periods ensure action potentials are spaced out, allowing for accurate signal transmission. They also prevent overlapping signals. The absolute refractory period guarantees that action potentials do not overlap, which maintains the integrity of the signal. Finally, refractory periods prevent the action potential from traveling backwards along the axon. This ensures that signals only move towards the axon terminal. So if we're going to compare absolute and relative refractory periods, just want you to remember that during the absolute refractory period, no action potential can occur regardless of the stimulus strength. The absolute refractory period corresponds to depolarization, because those sodium activation gates are open, and the repolarization phase, because the sodium inactivation gates are closed. The relative refractory period requires a stronger than normal stimulus to trigger an action potential. And this occurs during hyperpolarization because those sodium channels have reset. Why do they matter? Well, without refractory periods, neurons could fire uncontrollably, leading to chaotic and unreliable communication. For example, in the heart, refractory periods ensure that cardiac muscle cells do not contract too frequently. This allows for coordinated heartbeats. It also allows for the heart to fill up before it contracts again. In the nervous system, they prevent overstimulation and allow for clear directional signaling. So let's summarize with our key takeaways. Refractory periods are short phases following an action potential that limit or prevent the generation of another action potential. The absolute refractory period ensures no action potential occurs, while the relative refractory period allows one to occur, but it requires a stronger stimulus. These periods are essential for controlling neuronal activity, preventing overlapping signals, and maintaining unidirectional signal flow. So that's it for episode 13. I hope this episode has clarified the importance of refractory periods in neuronal signaling. Join me next time for episode 14, where we'll dive into the physiology of chemical synapses and how neurons communicate across a gap. Until then, keep questioning, keep exploring, and stay curious.